Hello, and welcome to this video. In this video, we're going to make a start on an introduction to gravitational fields. Now, fields is the biggest section of the A2 physics content, so it's split up into gravitational fields, electric fields, and magnetic fields. So we're going to treat them one at a time first, and then we should see as we're going along that there are some comparisons we can make between them, because most fields will behave in a very similar way. Not exactly the same, but similar. So we're going to start with gravitational fields. And before we actually get into the content of gravitational fields, we have to try and understand first what is this field thing? What does that actually mean? Now, it would be a good first guess to just describe a field as being an area where you can feel the force. If we know we're on Earth, there is a gravitational field around Earth because we're constantly being pulled towards the Earth. And this is effectively the idea of a field. If it's a gravitational field, we've already heard in particle physics that gravity is one of the fundamental forces. Okay, the four fundamental forces. And we said that gravity is too weak on a particle level to actually have any kind of effect on any interactions that particles have, because the mass of particles are so small that in comparison to the strong force, the electromagnetic force, and the weak force, this has no effect or negligible effect in comparison. So what we need to recall from that, the main point is what we should already be familiar with. Gravity acts on mass, right? So it's anything that acts on a mass. Okay. Now, the reason that I've used the example of the Earth is because that's when we get to mass scales that are big enough that we can actually start to observe the effect of gravity. This is why whenever you hear anything about gravity, it's always about Earth holding the moon in orbit, or having satellites in orbit, or the sun holding all the planets in orbit, and stuff like this. So the first thing we need to wrap our head around is, how does gravity work in this field? And to do that, we're going to visualize something called the field lines. Now, field lines are something that we can apply to all types of fields. So we have same for gravitational, electrical, magnetic. And I'm going to take two cases of field lines for gravitational fields. So we can have a radial field, and we can have a uniform field. Okay. Now, as a little disclaimer, there is no such uniform field for a gravitational field. It's not possible for us to actually form a mass that will have a uniform gravitational field. The uniform gravitational fields are approximations that we make. So this is an approximation based on the perspective. Okay, so based on where the person viewing this is. If we're on Earth, for example, if we're on the surface of Earth, we will see field lines that are uniform because we're zoomed into the surface of the Earth. If we were to then zoom out and go to the sun and look at the field lines on the Earth, we would then see a radial field. So this uniform lines are when we're zooming into the surface of a planet or something like this, but usually we will have a radial field. And this then brings up the point of what happens if I zoom so far out that my perspective completely changes, and instead of seeing the whole Earth, I just see a dot. And this is another approximation that we make called point masses. And we'll make the same for charges. And point masses basically just allow us to say that we've concentrated all of the mass on a single point. So we can basically neglect the idea that it is a sphere when we zoom out far enough. So we make the assumption that they are point masses. Okay, so we've zoomed out such that all the mass is concentrated in one position. Now, it might seem a little bit strange to do this at first, and the whole reason we can do this is because this is one of the core postulates of Einstein's theory of special relativity. So those of you who are going to choose the turning points option will look at this in more detail. For those of you who aren't, I'm going to give you a brief understanding of what relativity says, which is basically that the quantities that you measure, so the distance, the speed, the time, the energy, is dependent on where you're looking. Okay, so that's why it says that this is the speed relative to the viewer. But in this case, if we change our position, one of the two postulates of special relativity is that the laws of physics are the same in all reference frames. So it doesn't matter where you stand in the universe, doesn't matter where you're observing from, the laws of physics, so things like Newton's laws and all of this kind of thing, have to always be satisfied. The approximation that we're making here, being a uniform field and being point masses, is just basically to simplify the maths a little bit so that we can get a large scale overview of what's happening, and then we'll zoom in and then see what actually happens inside the Earth and how the gravitational field changes. But for now, let's start with just a point mass for this radial field. So let's say we've zoomed out far enough that this planet or Earth or the sun or whatever this might be just looks like this dot here. Now the field lines in gravitational fields will always point towards the mass. Okay, so they point in the direction that the force will travel, and we're going to look at a video on the gravitational field strength to actually see why we must do this. So our radial field, we can have it's radial because we're going to end up with a circular type of field, and then all of these lines are going to point towards the mass at the center. And this is a radial field. So this is the approximation we make that when we zoom out far enough. Now, another thing that we need to know about these field lines is they never end. Okay, we said in the particles video, the range of gravity is infinite, which means we can't actually ever escape a gravitational field. We have to go to infinite distances to actually get the force that we feel to be absolutely zero. So it means that this is an infinite range. Okay. And so usually when you see these diagrams like this, you have to draw boundaries on this, because obviously I don't have infinite space to draw infinitely long lines. So I'm just going to say, if I just look in this boundary, this is what the field lines look like. Now I can do the same for uniform, but now we have a flat surface because, like I said, we've zoomed in. So this is the surface of the Earth. And the field lines, when we zoom into the surface, we know that all things, if we drop them, the direction that they're going to move due to the force of gravity is just straight down. So we will say that we have field lines that look like this, where they all point downwards. Okay, and again, we have to put some sort of boundary around this so that we can specify that these lines don't actually ever end. Okay, they only end when they touch the mass. Okay, so this is your two setups. Now for the majority of these things, we're going to neglect the idea of uniform fields. When we take on the idea of it having a uniform gravitational field, everything will just revert back to everything you've done in AS mechanics. The forces due to gravity is just going to be mg, it's just your weight and things like that. That's not particularly interesting anymore. We've been through that, we understand that, we want to learn new, more interesting things. So most of what we do is actually going to be looking at radial fields. And we're not only going to be looking at how a radial field forms when we just have one mass, because we know in nature we never just have a planet by itself. We have a planet with a moon orbiting it, with satellites orbiting it, with sometimes things like Jupiter or Saturn, you have multiple moons. So we can have different bodies in this same space. So how do the field lines look when we have two bodies that might be co-orbiting each other? Some of you might be familiar with the discovery of gravitational waves, or the observation of gravitational waves, and that was due to co-orbiting black holes. So we can have two massive bodies, two black holes that will actually orbit each other until they eventually collided, and that's when we detected the gravitational waves. So let's draw an image of that. Let's say that we have two bodies. Now, another thing with gravity is an attractive force. So gravity is always attractive. Okay, there's never anything that we can observe where we have two masses that are repelling each other. Okay, that will happen with electric fields because we can have two charges that repel each other, but with gravitational fields, everything gets pulled in. Okay, so let's say that this mass here, I'm going to draw it a little bit bigger, but still treat it as a point mass. Let's say this is Earth, so let me put a little E here, and then let's say that this mass here is the moon, so let me put a little M there. And we want to visualize what do the gravitational field lines actually look like between these two bodies. Well, we know that both of these will exhibit a radial field. So we can start off by saying that we know that it's going to look something briefly like this for now. Okay. And we also know that this one will have something similar, like this. So we have two radial fields. I'm not going to draw the direction of them yet. But we also know that the Earth and the Moon attract each other. Okay, so this line here is actually going to connect with this line there. So I'll get rid of that. So these two lines will connect together. And then actually these two lines will also connect, but with more of a curvature. And so will these two. And actually most of these lines will connect. But I am going to just simplify this down to just having these, and I'm not going to draw the boundary, but you would have to make sure you have a boundary on this. Okay, now all of these ones are going to point towards the Earth, and all of these ones are going to point towards the Moon. In the middle, it's attracted to both of them. So this is almost like a tension force. When we've pulled a rope in two different directions, we'll have part of the force going towards the Moon, but we have an equal force going towards the Earth. Okay, so we actually have two directions, and so this is what happens. We always have attractive forces, and so we'll end up with some kind of diagram that looks like this. Now, it is quite common for them to ask questions that involve multiple bodies, and the final thing that I'm going to look at is this idea of a positive test mass, or actually, we know it's always going to be positive. Let's just call it a test mass. When we're defining quantities in fields such as the field strength or the potential in a field, we have to introduce this idea of a test mass. So we're saying a test mass is basically some arbitrary small mass. So arbitrary meaning that it doesn't matter what the value of it is, it's just any kind of choice will work in this case. So arbitrary small mass. And the whole idea is, if we were to put that test mass in this position in the field, so if we were to, for example, have another radial field where we have this kind of effect, let's say we were to put in, we wanted to calculate, I don't know, the potential, and we'll see how to calculate the potential at this point here. We would say if a test mass was there, if a test mass was there, what kind of potential would it feel in this position? Okay, now we can do the same thing if we have two bodied systems, and we say, okay, what would happen if the force at this point, if we put a test mass at this point here in the middle of these two, which direction is it going to get pulled in? Now you can immediately use your logic and say it's definitely going to get pulled to the one with more mass. So we would logically be able to say that it's going to get pulled towards Earth, but this is physics. We have to put numbers in. Okay, so while we already know the answer, we have to say, okay, we know the force is going to go in this direction, but how much force is it going to go in that direction with? Is it possible that it's going to have so much force that it's actually going to collide with Earth when it gets there? And this is a everyday occurrence. We get meteorites and asteroids that we can spot having a trajectory towards Earth all the time. We basically just do a calculation like this to see, are they going to strike Earth? Will they fly past Earth? And then we know how to prepare or just be ready if anything like that were to happen. Okay, so this is your introduction. The things that you want to take away from this are how field lines look. So we have the fields of having radial fields are what we're going to look at mostly, but we can say we can make an approximation of a uniform field. We say that we usually will work with point masses. The only case where you won't work with point masses is going to be when you're looking at forces inside the body. Now, this doesn't come up often because it can get a little bit complicated, but I will go through it just to give you the general idea. And then this idea that when we have two bodies, their field lines will interact with each other and they will join together. And then this idea of a test mass in order to visualize or imagine what a certain electric gravitational field strength or certain gravitational potential would be at any point in a radial field. Thank you for watching.